Okay, today we're going to technically take two notes, but one of them is just an introduction. So, very quickly, I wanted to remind you that Unit 1 is all in red titles. Okay, I've said it in the other video, but I want to make sure we're good. Unit 1 is going to be in red titles. That way we can keep it straight. Okay, so this may be page 2 for you. This may be page 4. Whatever page this is, put your page number. We're going to talk about an intro to three variable systems first. Make sure you put today's date. And then we're also going to be solving this three variable system by substitution, which is why we reviewed the Algebra 1 two variable systems last time. Okay, so let's move on to our notes. So this is my next page. So this will be, I think it's page 3 for me. So I'm going to put 3 on the right and make sure I'm going to color it with a little red spot so I can flip to it later. And I'm going to title it Intro to Three Variable Systems. I will get to those pictures here momentarily. You do not have to draw them. Please do not try to draw those. I did draw mine and it took me forever. So first of all, let's talk about the three-dimensional space and solution types. So I'm just going to put types of solutions here as my first little section. So types of solutions, I don't know if the highlighter helped, but I'll highlight it, are the same types as we had in two variables, but they just look a little different. So first, let me talk about what the three-dimensional space looks like. So the two-dimensional space, you're used to an x and a y, very simply here. Well, the two-dimensional space takes this and like flattens it out like it's on the floor. So what happens is your x-axis is actually here, your y-axis is here, so this is x, this is y, and your z-axis, that's the third dimension, actually goes up. So if you look, this is kind of like the corner of a room. There's your x, your y, and your z-axis, okay? Coordinate points on here are not just x, y. They have an x, y, and they have a z. So if we talk about, let's say, this point here, I'm trying to find the best way to draw it, this coordinate point would be the ordered triple x, y, and z. Notice they're still in alphabetical order. So the x component would be, let's see, I'll do that in green. The x, actually, let's do z first. Z is actually a little easier. So z is going from this point straight down onto the xy plane. So this would be the z component. Then you have the x component, which is perpendicular to the x-axis. This is that's actually your y, because you're going up this high. So you'd be like 1, 2, 3, 4, 5. Sorry, I messed you up. This is actually your y, because you're kind of following your y-axis. How high do you go? And lastly, your x is left to right this way here. That's your x. So it's like you're going 1, 2, 3. Okay. Z's are up and down following the direction of the z-axis. So that's how you would write this coordinate point. Now, luckily, we're not going to do a lot of graphing by hand in 3 dimensions because this is not quite the easiest thing to do. I just need your brain to think a little differently. Okay. These are no longer lines. These are planes. So I'm going to draw another set of axes. I'm going to draw another set. Z, Y, and X. Okay. If you look right here, it kind of makes a little square. Let's see. See how it kind of makes a little square on that side? That's a plane. Over here, it kind of makes a little square. If I continue this way and this way, that's a plane. And I can have another little plane right here. So it's kind of like a cube, kind of, sort of. So we're not talking about lines anymore. We're talking about planes. So that's why these pictures look like squares. These are all different planes. So these are the three types of solutions you can have. On the first case, this is your regular one solution type. Basically, the important part about this picture is that all planes cross at that single point. All planes cross in one point. Cross at one point. That's still one solution. This coordinate point, x, y, z, is your solution. Solution option number 2 is you can cross at many points. So like the here, 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 and here. And mind you, these planes go out in all directions, up, down, left, right. So what this actually makes is these planes intersect in actually a line. So this is our infinite solutions, where you've got multiple points of intersection. And then finally, we have the no solution case, where all three planes don't cross the same point. So this one here is the simplest version of no solution because none of those planes are crossing. So none of those have any point in common. This is a little more complicated. So if you look at this spot here, that is the green and the red crossing, but not the blue. You're missing one. This is blue and red, but not green. And this is green and blue, but not red. So you're missing a plane on every one of these. Same thing here. This is green and red, but not blue. This is blue and red, but not green. So that's why these have no solution. Okay, we're not going to be drawing these much. We're more of just I want you to visualize the space that we're in. Now let's talk about how to check for solutions. Checking for solutions. So the way you check for solutions is you're basically substituting an ordered triple into your equations. So that's your first step. Substitute, I'm going to put sub, given point into, so given PT point into all equations. And notice how I'm abbreviating. I'm not writing every word out. Then you have two cases. If all are true, that means that yes, that point is a solution. Actually, let me actually write that out in case you look at this 3 days from now and forget. So all are true, yes, the point is a solution. Point is a solution. That's what we want. B, you could have at least one of them is false. That means that no, that coordinate point is not a solution. So those are the two cases you have. Okay, so let's try an example. So let's do example 1. So we're going to ask, is the point 4, -5, whoopsie, I'm used to a 2, it's actually 3 coordinate points. Is the point 4, -5, 1 a solution? 2. And then here is our system. It's going to be a larger one. 2x plus y plus 5z, there's my third variable that's new, equals 8. -x minus 2y plus z equals -13. And then x plus 3y plus 2z equals 9. Let me fix that x for you. So we're going to check if the coordinate point that I gave you is a solution to this system. You may see brackets like this around the system. You may not. It just depends on what book or what website you are looking at. So here's how we do this. We are going to substitute x, y, and z into each one of these equations and look for a true statement. So I'm going to start with equation 1. So for equation 1, we're going to check 2 times the x value is a 4 plus the y value is a -5. Notice I still put parentheses when I substitute it in. That will help you keep these negatives and minuses and positives straight. Okay, and then plus 5 times z, which is a 1, equals, hopefully, 8. Now you're left to do is just simplify. 2 times 4 makes 8. A +1 times a -5 is a -5. And then 5 times 1 makes 5 equals 8. Well, -5 plus 5 makes 0. So we have 8 equaling 8. So yes, this is a true statement. So far, this coordinate point is a solution, but it may not be true for all 3. Got to check all 3. So equation 2, negative of whatever x is, which is a 4, minus 2 times whatever y is, which is -5, plus z, which is a 1, hopefully equals -13. And let's check. Negative times a 4 is -4. -2 times -5 is a +10. and then you just have plus 1 equals negative 13. Well, we have 10 plus 1 makes 11. So negative 4 plus 11 equals negative 13, which is not the case. 11, this makes 7. Well, 7 does not equal negative 13, so that means this is actually false. So we can stop here. Once you hit a false statement, that means that the coordinate point for negative 5, 1 is not a solution. That's what that would mean. Once I hit a false statement, that coordinate point is not a solution. If this had been true, then you would need to go check number 3 with the same way. Substitute x, y, and z and see if you get a true statement. True for all 3 means yes, it's a solution. False for at least 1 means not a solution. So let's try, I want you to try example 2 on your own. So this would be page 4. So this would be page 4 for me. So I want you to try example 2. So for example 2, you have the system. We'll do the question first. Is negative 2, 3, negative 6 a solution to, and then here's your system. Negative x plus 2y plus 2z equals negative 4. 4x plus y minus 3z equals 13. X minus 5y plus z equals negative 23. So here's the system I need you to check. And you should come out with the answer of yes, it is a solution. But I want you to go through the process and see if you can make sure you get yes.